Hi, we're going to talk about chapter 3. So let me just start by pulling up the slides. 14. Okay, so we've learned a lot of new ideas, a lot of new names for things, learned about the periodic table. Now we're going to think about chemical reactions in a little bit more detail, and we're going to think about how you determine when you have equal equal reactants to react with each other, and how do you answer questions like, if I have some reactant, how much product will I make? So we're going to look at the relationships between masses in chemical reactions. And so we'll go through this, and then in class I'll work a lot more examples, and you'll work some examples too, so that will help solidify it. It's really just one concept in this chapter, and we'll be introduced to that up front, and then we'll use it in a lot of different situations. So if we want to represent a chemical reaction, we can think about it on different levels. So this particular equation says that two molecules of hydrogen gas react with one molecule of oxygen gas, and from that you can make two molecules of liquid water. So that's on the microscopic level. So it's really telling you the number of individual molecules that have to react with each other to make another quantity of product. So you can think about that on the molecular, which is the microscopic level, but you can't measure a molecule, so you're not going to go into the lab and measure out 1-2 molecules, so 2 molecules of hydrogen and 1 molecule of oxygen. Instead, you're going to go and measure some mass, and it'll be a larger quantity of molecules. So you could also think about this on a macroscopic level of saying 2 moles of hydrogen gas reacts with 1 mole of oxygen gas to yield 2 moles of liquid water. So makes sense. If you have a molecule ratio, it's going to be the same mole ratio, because a mole is just a way to group molecules. So first thing we have to do when we want to decide how much we need to mix, for example, in this reaction, how much sodium would we have to mix with a quantity of chlorine in order to make it all into sodium chloride? And so before we could even answer that question, this reaction has to be balanced. So here it's showing you a balanced equation where 2 sodium atoms reacts with 1 diatomic chlorine molecule. And from that, you make 2 ionic formula units of sodium chloride. And so the way you balance it is exactly what they're showing you at the bottom of the slide, which is that you have to have equal number of atoms of each element on each side of the equation. So if you start out with 2 atoms of sodium and 2 atoms of chlorine, you have to make it into something that also has 2 atoms of sodium and 2 atoms of chlorine. You can't create and destroy atoms within chemical reactions. You can remember in nuclear reactions, we sometimes do change elements into other ones, but we're not going to talk about that here. We'll talk about that again when we look at chapter 8. So when we balance this particular one, it's just a little bit more complicated formula for things. So we have mercury 2 nitrate reacting with potassium iodide to make mercury 2 iodide and potassium nitrate. So the molecules, in this case, they're not molecules, they're ionic formulas, are a little more complex, but you still balance it the same way. You have to have 2 mercuries on each side, 2 nitrogens on each side, 6 oxygens on each side, 2 potassium and 2 iodine. And if you count them all up, they're now in different locations in different formulas, but you still have them all accounted for. So in order to balance these, you're going to write the unbalanced equation using the correct chemical formulas for each reactant and product. So if it's hydrogen gas and oxygen gas reacting to make water, you have to have the formulas right. It's H2. When you find hydrogen, it exists as a diatomic. When you find oxygen, it exists as a diatomic. And water is H2O. It's 2 hydrogen atoms for every 1 oxygen atom in a molecule. So we start with that. And then we don't want to change what our chemical formulas are, because that would change what was reacting or what was being formed. So instead, you just put coefficients out front to say how many molecules have to react to get your equation balanced. So you have to put a 2 out front of the hydrogen, and that gives you a 2 out front of water. And then if you count up the oxygens and hydrogens, they're equal on both sides of the equation. And after you do that, then you should have the smallest whole number ratios. So if it's 4 to 2 to 2, or 4 to 2 to 4, you can divide each of those by 2 to get 2 to 1 to 2. So that's the most correct way to balance that equation. Then you're always going to check your answer by making sure that the numbers and the kinds of atoms are the same on both sides. So they've already demonstrated that by, you always look and you say, okay, 2 hydrogen molecules gives you 4 total hydrogen atoms. 1 oxygen molecule gives you 2 oxygen atoms. And on the water side, same thing, 2 molecules of water is 4 hydrogens and 2 oxygens. So now if we're going to think about measuring these things in the lab, we're not going to measure out molecules. We're going to measure out masses. The most common way to measure out how much of something you have is by taking its mass. And so in order to then convert that to how many atoms, molecules, or moles we have, we need to have a conversion factor. So the molecular mass or the formula mass is going to be that conversion. So if you sum up all the atomic masses of all the atoms in a molecule, for example here, HCl, if 1 hydrogen atom is 1.0 atomic mass units, and 1 chlorine atom is 35.5 atomic mass units, now you have a molecule that has the hydrogen hooked to the chlorine. That means that 1 molecule is going to be the sum of those 2 atoms, so it'll be 36.5 atomic mass units. Same thing if you have larger molecules. This is ethene at the bottom. So you have 2 carbons and 4 hydrogens. So each individual ethene molecule has an atomic mass of 28.0. A molecular mass is a very specific way, because we know molecules are covalently bonded compounds, but we also are going to be dealing with ionic compounds. And so it's more correct to call it the formula mass, the sum of the atomic masses of all the atoms in a formula unit of any compound, whether it's molecular or ionic. So when you think about how you can use that number, so how you can use the formula mass, if we have a mole of HCl, remember you would have the mass in grams would equal a mole. So that's something we learned about in chapter 2. So 1 mole should equal 36.5 grams of HCl. And so that also tells us a mole is Avogadro's number of particles. So it's just a way to group particles. It's like a dozen, except atoms and molecules are so much smaller. We're going to use a bigger number. So Avogadro's number is equivalent to a mole. So that is 6.022 times 10 to the 23rd molecules equals a mole. Therefore, that's how many molecules you would have in 36.5 grams. You can do that same math with the ethane. So now when we talk about this idea of chemical arithmetic or stoichiometry, stoichiometry is just a fancy word for the chemical arithmetic needed for mole mass conversions. So if you look at this generalized equation where you have little a moles of the compound A plus little b of the compound B going to little c of the compound C plus little d of the compound D. The A, B, C, and D are going to give us the stoichiometric ratios that we need. So if we start out with the number of grams of A and we want to figure out how much B you'd need, you have to first convert the grams of A to the moles of A. Once you get the moles of A, then you can relate it to the moles of B by that stoichiometric ratio. So if A and B, little a and B are both 1, then your mole ratio between A and B would be 1. But if little a was 1 and B was 2, then the ratio would be 2 moles of B to 1 mole of A. So we have to take into account the molar masses. So you have to use grams of A and then use the molar mass of A to convert that to moles. And then you have to compare A to B by using the ratio in a balanced equation. So let's just look at a specific equation. So this is sodium hydroxide reacting with chlorine gas. I'm not sure what that polyatomic is, but NaOCl, you could look that up on your polyatomic table. Don't think it's perchlorite, maybe. And then sodium chloride and water. And so the question they're asking in this problem is how many grams of sodium hydroxide are needed to react with 25.0 grams of chlorine. So it won't be 50, it's not twice the mass, it's twice the number of moles. So we start out with the grams of chlorine, we use the molar mass of chlorine to convert that to the moles of chlorine, then we're going to use a ratio of 2 moles of sodium hydroxide to 1 mole of chlorine. And then once we have moles of sodium hydroxide, we can use the molar mass of sodium hydroxide to convert that into grams. So here are those numbers. So if we have 25.0 grams of chlorine gas, 1 mole of chlorine gas is 70.9 grams. So that's 2 times the atomic mass of an individual chlorine atom, because Cl2 has 2 chlorine atoms per molecule. So at that point, if you look at what you have, you cancel grams of chlorine and grams of chlorine, and now you're at moles of chlorine. And now you look at your balanced equation to see that it takes 2 moles of sodium hydroxide for 1 mole of chlorine. So in that step, you're canceling moles of chlorine, converting it to sodium hydroxide. Your last step is going to be take the formula mass of sodium hydroxide. So 1 sodium plus 1 oxygen plus 1 hydrogen is 40.0, and that's how much is in a mole of sodium hydroxide. So at that point, if you look at what you've canceled moles of sodium hydroxide on top and bottom, and you finally have 28.2 grams of sodium hydroxide. So what we've calculated right here is theoretically how much sodium hydroxide would it take. Oftentimes reactions don't go to completion, or for some reason you don't actually make this theoretical comparison. So when you're comparing how much product you can make from a reactant, you'd first calculate the theoretical yield. So if we went back here and we could have said how much sodium chloride can we make from 25 grams of chlorine gas, we could have done the same calculation, except rather than converting it into sodium hydroxide, converted it into sodium chloride. And then you could ask the question, okay, theoretically, the quantity of sodium chloride that we could make is the theoretical yield. But then you'll go into the lab and you'll actually do the reaction and measure the mass, and it will almost always be slightly less, or sometimes a lot less. And so that would be your actual yield. So the percent yield is what you actually made divided by what you should have been able to make theoretically if every molecule reacted times 100. Another thing to think about is that usually if you just mix some things together for a reaction, you don't put them in the correct ratio. Sometimes it's because one is expensive and you want to make sure it all reacts, so you put some excess of the other in. Or one is really toxic and you want to make sure it's all used up. So usually you mix up things that aren't in the correct ratio for all of them to react. So the limiting reactant is the reactant that's present in the limiting amount. So the extent to which the chemical reaction takes place depends on this. So that's like saying I have a dozen eggs and 5 cups of flour, and I want to make a cake that takes, I want to make as many cakes as I can that take 2 eggs and 2 cups of flour. What's going to limit? And if you do that math, it's easy to see it would be your flour. The flour will limit. You'll have excess eggs left over. So the excess reactant is any of the other reactants still present after determination of the limiting reactant. So it's going to be something that doesn't all react. So in the cake situation, it would be something like the eggs, which are left over. So when we look at a reaction, so this particular reaction is ethylene oxide, and it reacts with water to form ethylene glycol, which is antifreeze, and it's also a starting material for making polymers. So because water is so cheap and abundant, it's used in excess when compared to ethylene oxide. Ethylene oxide probably came from petroleum, so from crude oil out of the ground, and you separate the components. So it's a more expensive and important, I would say, environmentally important reactant. And so if you want to make sure you use it all up, you're going to put in excess water. So at high temperatures, this is the reaction. They're just giving it to you again and showing you the stick structure and the space filling structure, so you get an idea of what those molecules look like. You can check quickly and make sure that the reaction is balanced, because you want to make sure you always do that. And then the question we're going to ask is, if 3 moles of ethylene oxide react with 5 moles of water, which is limiting and which is present in excess? Given they're starting with moles, that's a pretty easy question. If ethylene oxide reacts 1:1 with water, and you only have 3 moles of ethylene oxide and 5 moles of water, you can immediately see that the ethylene oxide is limiting, and we're going to have 2 moles of water left over. They're just giving it to us again and doing the math that I just did on the previous slide. So 3 moles of the ethylene oxide, if it reacts with 5 moles of water, only 3 moles of the water can react. And so you'll make 3 moles of the product from some of the water reacting with all of the ethylene oxide, and you'll have left over 2 moles of water. So this is another one, lithium oxide. So Li2O, it's used aboard space shuttle to remove water from the air supply, and they give us the equation and they've balanced it. It asks us the question, if we have 80 grams of water that we need to remove, and we have 65.0 grams of lithium oxide is available, which is going to limit, and how many grams of excess reactant remain, and how many grams of lithium oxide are produced. So we'll start out and we'll calculate how many moles of water could react with 65.0 grams of lithium oxide. So in the first step, we take the 65.0 grams of lithium oxide, we convert it to moles of lithium oxide with the formula mass of 29.9. And then we look back at our balanced equation to see that it takes 1 mole of water for 1 mole of lithium oxide. And so that tells us that we have 2.17 moles of water that would be needed, or that could be removed from 65.0 grams of lithium oxide. And so now we're going to look. They also told us that we have 80 grams of water. So 80 grams of water, convert that into moles. What we have present is 4.44 moles of water. And so lithium oxide is what's limiting. We can only react away 2.17 moles of water, but yet we have 4.44 moles of water. So how much water remains? We'll start out by figuring out how much water reacts. So this says that if all the lithium oxide reacts, we will have reacted 2.17 moles of water. So we're going to take that 2.17 moles of water, convert it back to grams. And so we will consume 39.1 grams of water. We started out with 80. So initially we had 80 grams of water. 39.1 grams were consumed by the lithium oxide, and therefore 40.9 grams of water are in excess and will still be present. How many grams of lithium oxide are produced? So if we can make 2.17 moles of water, you make 2 moles of lithium oxide for 1 mole of water. Then we have the formula mass of lithium oxide of 23.9. So that's 1 lithium plus 1 oxygen plus 1 hydrogen. So 23.9 grams per mole. And if we do that math, we get 104 grams of lithium oxide. So all we've been is using the concept of mole, and that if you have the mass of a substance, you can use the formula mass to convert it into moles, and then you can compare what reacts in a reaction because you actually have the number of molecules or the number of atoms. So this second type of problem is one where we're going to try to figure out what a formula is. So we'll go through this and that will hopefully make sense, but it's really just an example of another example of using the relationship between mass and moles. So the percent composition is expressed by identifying the elements present and giving the mass percent of each. So we'll go through a problem to make that less abstract. The empirical formula is the smallest whole number ratio of the atoms in the compound. And then the molecular formula tells us the actual number of atoms in a compound. It can be either the empirical formula or a multiple of it. So for example, something like carbon monoxide, CO, it tells you the simplest, smallest whole number ratio of the atoms in the compound. So that's an empirical formula, but that's actually the molecular formula too, because there is only 1 carbon and 1 oxygen in carbon monoxide. Whereas if you have something like peroxide, peroxide is H2O2. So the empirical formula, if you want the smallest whole number ratio, would be HO. There's 1 hydrogen for 1 oxygen. But the molecular formula is twice that. They're H2O2. So the molecular formula is always some multiple of the empirical formula. So we start out with this problem. It's fairly easy. It tells us that we have a colorless liquid and we want to know what its formula is. It's 84.1% carbon and 15.9% hydrogen by mass. So usually if you're given mass percents, the easiest thing is to say, I have 100 grams of this colorless liquid. That would mean I have 84.1 grams of carbon and 15.9 grams of hydrogen. From that information, we want to figure out what the empirical formula is. And it tells us that the molar mass of this compound is 114.2. So from the empirical formula, we'll also determine the molecular formula. So we start out, as I said, and it's easiest just to say 100 grams would mean 84.1% is 84.1 grams. We convert the grams of carbon into moles of carbon, the grams of hydrogen into moles of hydrogen, just using the atomic mass. And then what we end up with at that point is we have the ratio of carbon 7.01 to hydrogen 15.9. And we want it to be whole number ratios. So the easiest way to get there is to divide each of those numbers by the smallest. And so if you have a ratio and you divide the numerator and the denominator by the same number, you haven't changed the ratio. So we end up with C1, H2.27. So now we have simple numbers, but they're not whole numbers. So in order to change those to whole numbers, 2.27, if you multiply it by 4, will give you 9. And then you'd also have to multiply the 1 for the carbon by 4. And so you end up with the empirical formula of C4H9. We saw in the problem that the actual molecules, molar mass is 114.2. And so if you have 114.2 and you divide it by 57.0, 57.0 is the mass of C4H9, the empirical formula. So we're checking to see how many empirical formula units go into the molecular formula unit. So 114.2 divided by 57.0 gives us a 2, and therefore the true molecular formula is twice the empirical formula. So that means it's C8H18. So that's actually, if you looked at a molecule of this compound, it has 8 carbons hooked together somehow and 18 hydrogens attached. So one of the ways to get information about how much of each element is in a compound, if you're trying to figure out what the empirical formula is through something called combustion analysis. So that just means you react it with O2. That is the reaction of combustion. So we have a new hydrocarbon and we want to know how much carbon and hydrogen is in it. And so we're going to react it with oxygen. We make all the carbon into carbon dioxide and all the hydrogen into water. And then you can figure out if you have a mole of carbon dioxide, then that means you have a mole of carbon in the compound. But if you have a mole of water present, that means you have 2 moles of hydrogen. And so it'll be very similar to our last problem where we were looking for the formula with percent composition, but now you have to relate it to how much carbon dioxide and how much water there is. So I'll do a problem like this in class. They're sometimes a little bit confusing, but the concept is exactly the same. All we've used in this chapter is the concept of grams can't be compared, but moles can be compared. So one of the ways that you figure out the percent composition is by using a mass spec. So a mass spec is described in your textbook and you can look at it. It's based on the idea that if you have electric field and you are shooting your molecules from one end of this tube to the other and you put in a magnet, charged particles are influenced by a magnetic field and they're influenced based on how charged they are and how fast they're going. So if you have heavy molecules going through, then they're going to be going slower. And if they have more charge, they're going to be more impacted by the magnet. So that will determine where they end up on the other end of the tube. So essentially it's a way to determine what's in a molecule, so what a molecular mass is. And that is all of chapter 3. We'll definitely work hard on these examples because chapter 3 is really best learned by working examples. You're looking at the arithmetic of chemical reactions, so makes sense. It should be something that you do a lot of examples with. So see you for chapter 4.